In this combined lecture 23rd and 24th, we continue our discussion on solving elliptic equation once again, and we try to go back historically to the Jacobi method and point out that some of these point iterative methods are more amenable to parallel computing, and having identified that, we also discuss about the convergence properties of these methods, which relates to diagonal dominance property of this associated A matrix, which in turn determines the spectral radius of this diagonal dominant matrix. In this context, we are going to talk about a theorem which is attributed to Stein and Rosenberg. We will pick up some model problems and explain the Stein and Rosenberg theorem. We notice that there are other possibilities of accelerating the convergence, namely by relaxation methods. These are built upon around those basic methods that we already talked about. So, in this relaxation methods, which are also known as successive over relaxation methods, we are going to talk about an SOR method or successive over relaxation method on the Gauss-Seidel basic methods. We find out that there are ranges of this relaxation parameters that is given by this Ostrowski-Varga theorem, which says that this parameter has to be between 0 and 2. And once we have figured out how to accelerate the convergence, we try to quantify this convergence criteria or the performance parameter of iterative methods. That is what we are going to talk about. And in this context, we see that some of these line iterative methods could be further improved, and a new method was enunciated in 1950s, which is called the alternative direction implicit method or ADI method. This is how we are going to switch over from classical method to a method which is found to be quite efficient. You would find that Jacobi method is still used for solving some of this classes of problem, because you do not really need to pass on the information as the iteration progresses from the neighboring nodes. You know, one of the major problem in parallel computing is I/O, input output processes. I/O processes actually reduces the speed, and sometimes it can lead to what is called as a latency problem. So, maybe one node is done, but it is waiting for the neighboring nodes to complete that sequence of work and pass that information, then only you can proceed. So, some nodes will be active, some will be inactive. This is a problem of latency that comes about, and that is not visited upon when you are actually using Jacobi method. So, please do understand that it is not a historic discourse. We still have utility for methods like Jacobi method. So, for Jacobi iteration for this equation A x equal to b, we split the A into 3 parts, and this is not same like what we talked about in that particular example of A1, A2, A3 matrix that we have talked about. Here it is a much more of a general problem. So, this A matrix is split into a strictly lower triangular matrix that we identify as L. Then we have a D matrix, which is the diagonal matrix, and U is the strictly upper triangular matrix. So, when I write L and U on the diagonal, there are no non-zero entries. Those non-zero entries are strictly put into the D matrix itself, right. Now, we also know for the Jacobi iteration, we do that iteration where we take that new matrix, which replaces the original A matrix, is given by the diagonal matrix itself. So, n is equal to D, and we have seen that G is given by I minus n inverse A. So, n is D. So, this is D inverse A. The I itself I could write it like D inverse into D, right. If I do that, then I can factor out a D inverse, and I get this. What is A minus D? A minus D is nothing but L plus U. So, we have an expression for G matrix which looks rather clean, as given in the last equation 45. All you need to know the diagonal split matrix and the sum of lower and upper triangular matrix. And this we have already stated that error goes by multiplication of the G matrix, and what we can say that E of k would be written in terms of G into E of k minus 1. Now, what we can do in writing out in component form, what we actually do is basically we write it like alpha ii into ei, and everything else other than the diagonal entry is put on the right hand side, and that is what you have it in this square bracket in 47. So, starting from E1 to En, they are at the previous level and multiplied by the entries of that A matrix at A or G or whatever you say. That is how you get it, right. So, this is how we get. Now, what you notice that we can define a parameter which I call as theta I, which is nothing but these quantities that are inside the coefficients alpha I j, and everything is divided by the diagonal entry. So, that I write it as alpha I I. So, what happens is what we are seeing that the error at the ith point at the kth iterate depends on the product of these theta i's times the error at the previous step. So, what does this parameter indicate? The parameter actually tells you how each of these quantities different points, different errors are contributing to the error at this kth level, right. So, if I have this quantity very small, that quantity that particular component of E at the previous level does not contribute, while if this point is very close to 1 or more than 1, then I can see that that quantity actually gives more contribution. So, what happens is this ratio theta I basically tells you the role of the coefficient vis-a-vis the corresponding diagonal component, right. That is what it is. So, what happens is given a matrix A, then you should start looking for what is this ratio going to be. If this ratio is less than 1, that means what? It will contribute lesser and lesser at the subsequent level. That is what it means. So, this property is called the property of diagonal dominance, right. So, I could basically define a based on maximum principle some kind of a error norm, which I have called here at E of k. That is the maximum when I scan through all the entries of that E k vector, and then we have this triangular inequality, right. So, I could write that the modulus of error at the kth point is less than that quantity that we defined as theta I. So, in 48 you can see this theta I is here, and that basically tells you that I could say that error at the kth level is bounded by error at the previous level times the maximum value of theta, right. So, this makes it a stronger case. So, if I scan through all theta and pick up the maximum, then this inequality will be even stronger when I replace this theta i's by theta max, right. So, that is what we have done. So, what happens is then we can see the convergence will be faster, the error will decay faster if I have this theta max itself is as small as possible. So, this is what we really want. This is what really want, that as we keep on going through this exercise of iteration, we want the successive error norm should keep coming down, and that will be ensured if this theta max is less than 1. So, if theta max is less than 1, then we can see this Jacobi iteration will converge, and this is what is called as the property of diagonal dominance. That means what? The diagonal entry dominates over all the off diagonal terms. Then of course, all the theta i's will be less than 1, and the maximum value is also less than 1. So, theta max is less than 1. So, this is what is called as the diagonal dominance condition for convergence of Jacobi iteration, and this is shown to be sufficient, and it has been also shown as a sufficient condition for Gauss-Seidel iteration. However, I will come back to you and show you some simple examples where I will investigate that in some cases Jacobi iteration converges, Gauss-Seidel does not, and vice versa. Okay. So, basically what does this diagonal dominance mean is that is also something similar to what we have already said. Theta max would be somewhat related to the spectral radius of the G matrix. We have seen, right, in the beginning of today that the spectral radius, the maximum eigenvalue, determines the convergence rate, and if spectral radius is less than 1 and you have a, or alternatively you have a matrix which is diagonally dominant, then both of them actually imply convergence. Okay. There has been some attempt in formalizing some of these results, and this has been stated by one of the theorem, that is due to Stein and Rosenberg, and which states the following conditions, that if I have a matrix with the following property, the properties are written like this, that the diagonal quantities are, let us say, positive and off diagonal quantities are negative, and in addition what we have is the magnitude of the diagonal is greater than the sum of the magnitude of all off diagonal terms. So, theta was measuring individual entities, but this theorem demands something more stronger. It says you take the off diagonal entries, obtain its magnitude, sum it over, accepting of course the diagonal part, and if this inequality is given, then it is strictly diagonally dominant, right. So, the diagonal is really overpowering everything. Now, it may seem too much of a thing to ask. I mean, how often would you get to that kind of a scenario? So, let us take a look at what we actually do. If you recall that the A matrix that we had written for the Laplacian, what we found that this A matrix had -4 along the diagonal, then we had +1 subdiagonal, super diagonal we had 1. I am just talking about a simple case of where delta x equal to delta y kind of a problem, and that is this. So, now if you look at many problems of computing, you come across the Laplacian operator, right, and this is the corresponding expression for the A matrix for the Laplacian, and you can see I could just take a minus sign whole through. So, then I could get the diagonals as all positive and off diagonal terms as all negative, right. So, in this case what happens, if I look at it say some line here, well, I have drawn it in such a way that I do not have all the 5 quantities together, but if I look at it, what I see that the diagonal term in those cases where I have all the 5 entities becomes equal to, see this sign here, there would be equal to sign, that is what is satisfied. 4 is sum of all those off diagonal terms. So, this is quite often obtained. In addition, if you look at some of the top lines or the bottom lines where you can actually find that this is missing. So, of course, this is a strictly diagonally dominant row, right, and the first line. The same way the last row, you can see it is strictly diagonally dominant, because this has become 4 and this has become 2, right. So, this kind of condition as demanded in this Stein-Rosenberg theorem is quite often met. So, this statement that strict inequality for some I is required, it is very often made, and the last condition 3 is irreducible. I suppose you can recall your earlier exposure on linear algebra. What is irreducible matrix? Well, it is that that the rank of the matrix is equal to the size of the matrix, right. That means what? You do not have any redundant equations, all the equations are linearly independent. So, in most of the physical problem that is how it should be. So, that is not a very strict condition to demand from. Now, if we have a matrix A with these 3 properties and we can estimate the gain matrix for the Jacobi iteration G j and the Gauss-Seidel matrix that I call it as G s, then we could have the following mutually exclusive relationship holding. The first condition which says that maybe all the eigenvalues of Jacobi and Gauss-Seidel iterations are equal to 0. Either that is true or both the methods are convergent, right. So, all the eigenvalues are less than 1, right. However, if you look at the sequence that when both the methods are convergent, the Gauss-Seidel is more convergent, right, because Jacobi lambdas are greater than lambdas for Gauss-Seidel. Okay. So, when both the methods converge, the Gauss-Seidel method seems to perform better, and that should be our expectation. That is what I told you in the beginning, that when I use more concurrent information, I should expect some improvement, but then provided that A matrix should have all those 3 properties that we saw in the previous slide. The second last case is where both the methods are neutrally convergent, means they do not reduce error, it just simply keeps on retaining it unchanged. In fact, in many of the practical computations you will see that is what is happening, that after a few iterations you see it does not change at all, it just remains like this. And the last condition says both the methods could be divergent, and if they are divergent you will find the Gauss-Seidel method is more divergent than the Jacobi method. Okay. It is a simple model problem. So, we are looking at a simple model problem. So, you should not have to really worry about, you could just simply invert the matrix and get the solution directly, but let us consider this via the Jacobi and Gauss-Seidel iteration. How do we solve it? Okay. So, basically what we are going to do is if I am doing a Jacobi iteration, what I would do, right. So, if I do this, what do I get? Let me start with some initial guess, and the easiest thing for me to do would be to take all of them equal to 0, right. Then what I am going to get from here, the next iterate k equal to 1, what I would get, x1 would be equal to 1, x2 would be equal to 3, and x3 would be equal to 5. So, these are basically these are the initial, and from the initial guesses we are obtaining this, right. Okay. Now, the next step, what would I get? So, you just substitute this value of x2 and x3, what I am going to get here. This will be 1 plus 10 minus 6, so that will be 5, right. The second equation would be equal to minus 3, and third equation would give us also equal to minus 3, right. And you look at k equal to 3, what we are going to get is this 2 will cancel out, so I'll get x1 of 3 equal to 1, and from the second equation I will get 3 minus 1 and plus 3. So this will also be minus plus 1, 1, and this also will become 1. Of course, there is no prize for guessing. That is the solution. You can see that all the equations are satisfied when I take this. So what it actually means that if you keep doing it further on, they will all be the same value, right? So what it shows that for this model problem, the Jacobi method actually converged in 3 steps. 3 steps, right? It did work that way. Now, if I move over and try to set up an equivalent Gauss-Seidel method, so what I would be doing, I would take, let's say, the first equation to evaluate x1. So if I call this as the kth iterate for x1, then I will probably have an identical step that what we had done for the Jacobi method. However, what will happen is when I come to evaluating x2, because it's a point, a Gauss-Seidel, if I already have something available, I will use that current information. So the x1 being evaluated here, I will put it like this, right? And of course, x2, did I write something wrong? None of you pointed out. So this will be x3 k minus 1. Okay, and look at the third step. That would give us what? 5 minus 2x1. This is available at the current level, so I could basically. So from here, I will use this information. Whatever x1 is made available via the current level of computation, we'll use that, right? So the same way, the x2 is evaluated, so I'll use it here. That's probably one of the ways. You can set it up in various other possible ways. I could do all kinds of struggling, and then what I would find that k equal to 0, we start off with again the same thing like before. Okay, you can keep doing, and you will find that this does not show any sign of convergence. So we draw the conclusion. So what happened is that even for such a simple system, for a 3x3 system, I have got this from one of the paper by Collins. Set this thing up to show that your Jacobi method converges, the Gauss-Seidel method diverges. So where do we lose the game? How did this happen? Was the previous theorem of any use? We just enunciated the Stein-Rosenberg theorem. What do we get? Look at the property of the matrix. Satisfied. this one is of course satisfied, it's irreducible. You actually lose out on the second condition in a very, very big way. The diagonal terms dominant, right? The way we have written it down, these are the diagonal entries of the 1, 1, 1. And you can see the off diagonal terms, their magnitude dominates over the diagonal entry. So you don't have the diagonal dominance. So of course this theorem does not work. Our initial conditions, the starting requirement of the property of A matrix are not satisfied. So that's what we are not going to make use of the Steiner-Rosenberg theorem, and we have to be aware of the fact. That's what I said, that apart from the property A, even this one we'll have to check if A is symmetric, positive, definite or not. How do you do that? If you remember how to check for that, what you do is you take that A matrix and you work out the various sub-matrices that you can from that, right? You can get this 3 by 3, 2 by 2, 1 by 1 matrices. And then when you take the determinant of those matrices, they all have to be strictly have to be equal to positive. That's when you call them as positive definition. And symmetry is, of course, you can this is not at all symmetric, of course. So symmetry is also violated. Diagonal dominance is violated. That's what we don't get it. Okay. Done that, we focus our attention to other things, other ways and means by which we can get the method work for us. And one of the ways that we can make even this iterative method work for us is by this relaxation methods. If you recall that we started off this iterative methods by solving this alternative equation. Remember, we changed A to a new matrix n, and then we worked upon the solution increment over iteration, and on the right hand side that is pushed by the residue. Okay, so basically residue is like a forcing, right? So residue forces the variation in UL plus 1 from UL to UL plus 1. That is driven by this quantity R, right? So this was observed, and we figured out that the spectral radius was given by I minus n inverse A. Remember, that's what we got if we adopt the equation 13. However, we could try to do something different. That is that we don't take the residue at each and every point as we have calculated. We actually give a overestimated role or underestimated role. So that what we do is we take the residue and multiply by a parameter theta, and that is what is called as the relaxation parameter. If less than 1, then of course we are under relaxing. So whatever the residue we have, we are taking a smaller component and forcing it to convergence, trying to converge. Or if we take theta between 1 and 2, then we have what we call as over relaxation method. However, in the literature, both this type of variants are called successive over relaxation method, or what we call as the SOR, successive over relaxation method. Okay. Now, why we choose the limit for theta to be between 1 and 2 for the over relaxation method is governed by a theorem due to Varga and Ostrowski, which we'll state later. But I can't just resist telling you the story that when Professor Southwell used to do this kind of work in Cambridge more than 100 years ago, then he used to actually use human operator to do this sort of calculations. So in a room, I may have narrated this story to you before, that you would make this human operator to represent the nodes in a grid. And then you go through this kind of exercise just now what I did. Remember, in the Gauss-Seidel method, I said, okay, first equation I used to calculate x1. And that information is required the person who calculates x2, because that's what was due to that operator, because you have to take the most current values, whatever is available. So what would happen, all these people would keep doing this. And Professor Southwell noted that if you actually say, okay, that's where the residue is maximum, and in this corner residue is minimum, so I would try to change, give more weightage here and less weightage there. Try to sort of equalize the march towards convergence by changing this. So basically, even talking about this theta that we have given, capital theta, would be position dependent. Someone will take more weightage, someone will take less weightage. And this used to go on. That's how this method was really worked out. But when you actually approach a computer, you don't do such a thing. You try to keep theta same for all the points. Otherwise, it becomes mind-bogglingly difficult, because you have to work out some kind of a strategy algorithm, how you relate this theta with node location. So basically, part is abandoned, and this is what is currently practiced. Well, about that story was, it had a tragic ending of that story, because Professor Southwell was a very, very, I would say, stern taskmaster. So he used to take away the salary for every mistake that someone makes. So what would happen in the room, everybody would compute, and every set of iteration would be over, then he would oversee and he would say, okay, now we can go to the next iteration. So that's how he used to do it. And in the process, he would find that some operator would have made some mistake. And of course, that destroys the whole flow of calculation. And so he used to dock salary. He used to take money away for making wrong calculations. And it is said, I'm not so sure, it's just a story, that some of them would went back with a deficit at the end of the day. So that's the sad part. But anyway, this is an example. See that how the subject is, where what computer does today, once upon a time, unfortunate human being is to do all that. And of course, what we can do is really, really fantastic compared to those days. Okay. Now, suppose we adopt that algorithm that we said, that n matrix working on the solution residue, and here I have put theta, and this is RL, right? So if I look at it, I could work it out. How did you define R? I forgot. Tell me, how did we do that? Ax minus b or b minus a? Does anyone remember? Huh? I don't know. I'm this is how I do it. I can plug this in here, and I can simplify. And what I find that I get this new iterate, UL plus 1, would be now I minus theta times n inverse A. Remember when we did not adopt relaxation method, theta was 1, right? So then we had the G matrix I minus n inverse A. So here what has happened by adding this degree of freedom by introducing capital theta, we have altered the gain matrix now, which is now a function of theta. Okay. So now what we notice, the gain matrix is given by I minus theta. Say. Okay. So this is the way we would like to do theoretical framework, obtain the G matrix like this. Operationally, what we do is that is given in equation 54. What you do is you have an algorithm. With the algorithm, you calculate U bar at L plus 1. That's why that over bar tells you that you have worked it out here. So U bar L plus 1 here. You surprised me. Okay. What we notice that this is the way we would adopt. We have an older iterate UL. We have just now calculated U bar L plus 1, and then we look at what the solution has changed. We multiply by capital theta with that, and we add it to the prior quantity. It's like what is called a character strategy in a predictor character approach. So any solution method is broken down into two steps. Okay, so you have a predictor method. You predict it the way any algorithm that you choose. Let's say it could be Jacobi, it could be Gauss-Seidel. You do that, and then you obtain that. So this U over bar L plus 1 is the output of the predictor stage, right? So now what you are doing, you are overlaying a additional correction, and that correction is obtained from this equation 54. So equation 54 is your corrector stage, and this is your chosen algorithm. So it's basically the method that you may like to adopt. You will do that. Now I have tried to show it to you. If I adopt such a method along with Gauss-Seidel point relaxation method, and I may say upfront, I have a feeling that some of these equations need modification. So please bear with me. I may actually put up the correct slides in a day or two. However, what you notice that suppose we are doing a Gauss-Seidel method, our approach has been like this, that if I am solving the problem in a domain like this, arrived at a point here, that may mean that the information available. This is what I have is I will call that as U bar level. So that level at the kth iterate here, whereas on this side I would continue to use the previous iterate. That is your Gauss-Seidel strategy, right? So if I do that, I tried to write that down, and I have a feeling that this equation may not be correct. This 55. I will have to take a look and mount the correct one for you. So that's you have a two-dimensional array, right? These are two-dimensional, but you have stacked it up as a one-dimensional array. That's what we do all the time. So when I write U vector here, basically it's a two-dimensional array written like a one-dimensional form, right? So that's what we do. So if I have now come to the ith node, so the predictor stage, what I'm doing when I have come to the ith node, I think that there is a Gij missing here. Please bear with me. There is a Gij which is multiplying the U's which are already been calculated. So that's what we are doing. The diagonal part has been taken to the left hand side, and any below that I write it like this, and anything that is above I write it in the second path. Okay. Now, so that is the way I calculate, I predict an update for all the points, right? That's what we are doing. And in doing so, we are actually adopting those values which are currently available in this first set of terms, whereas the second set of terms belongs to this part of the domain, right? So, following that predictor stage, we adopt the corrector stage. What we do is we do some simple weighting. What do? Whatever we have predicted, we multiply quantity by theta. Okay, so this is this part. So this part is nothing but the equation 55 itself. So take 1 minus theta times the previous accepted solution. So at the end of predictor and corrector stage, whatever I have, I call that the quantity without any overbar. So this is the previous iterate. Okay, so that I give 1 minus theta weightage and theta weightage to the currently calculated. And of course, you can write it down. What I have written in an algebraic equation form in 56, you can write it down in a matrix form, right? For example, UIK. What is UIK? UIK would be simply nothing but an identity matrix operating on the U vector, so that you just are picking the diagonal entry. That's what you are doing. And of course, 1 minus theta is a scalar quantity, and UIK minus 1, I have just written it like this, and theta times this operation. This operation, now you will understand what we have done. If you recall what we have done, we have taken this quantity times, remember that's what we did, alpha I into UI, and this we kept it on the left hand side, and on the right hand side, what I do is I write alpha ij, uj, and this is going to be j equal to 1 to n, and of course I will exclude j equal to I point, right? That's what we do. So this comes from where? This gives you something like your D matrix, diagonal entry. If I split that A into D, L, and U, then this quantity gives you alpha I gives you the D matrix, right? And this part, what we have done, we have split it into two parts. We have written it down like this, alpha ij and uj. Now j, I will go from j equal to say 1 to I minus 1. That is one path which are known, and then that would be at the current level. So that's what we are doing. Okay. Here I did not write it because I decided to write here for you in a detailed way. And then in the second part, I will start from the right of the point in question. So if I is the point in question, it will start from I plus 1, and this will take you all the way up here. And this part is also done like this, but this part is not known at the current level, so that's what we do. So you can see that this part, what is this part? If I write it, write A matrix as L plus D plus U, where would this come from? If you remember, if you take a look at this part comes in the lower part, lower triangular part of the matrix, right? Diagonal defines where I am. Anything below is the lower triangular part. Anything to the right and above belongs to the upper triangular part. So that's what we have done. So this part is done something like D matrix multiplying with U. So that is that. And this part, I will write it as L matrix operating on U. So I will write it as U of K, and there also let me write it this, and this part would be So basically that's how we have done. So d times uk is equal to L of uk plus u of uk minus 1. Having done that, of course, then what you could do, you can write uk would be nothing but d inverse L into this plus d inverse u into this, and that's what we have written here. You can see there is a d inverse L part, so this bracket has not been closed, and there is a d inverse u part that is operating at the previous iterate level. And then we have side equal to b, so we just keep on adding that. So there we may actually have added here a b vector. So that's what we have here, b, and there I will also have b vector. This sort of term, 1 minus theta operating on d and theta operating on u matrix, and that the last one is that additive part, the b vector. Okay. So right, I'm relaxing. I'm not taking exactly the same value as the residue has been obtained. I've just added an additional degree of freedom. So I'm relaxing. That comes from the previous equation that I wrote. Remember, and we have not taken what we have here. We have an algorithm by which we predict. That is what is given in 52nd part, right? So that part I am not taking what it is calculated as it is. I am taking a fraction of it or little more of it. That's what this theta indicates. So theta indicates whether I am taking what I have calculated, the whole of it or a part of it or more of it. That's what this role of capital theta is. Then to that, what I do is I already have some estimate of it in the previous level. So I take the rest of it is this. It's your something like your lever rule. You may have done it in your mechanics course. Say if I have one value here, another value here, about the fulcrum I take a balanced quantity from both the sides, right? So that theta is basically tells you about this relative size of the distances from the fulcrum to the ends, right? So think of your L as the left hand point of the bar and L plus 1 as the right, and the one that you are choosing by this method is where you are actually calculating the moment about the fulcrum. So this is exactly the same procedure. This always, whenever you adopt some relaxation procedure, you take it in a manner that it has to be consistent. What is the consistency condition here? Consistency condition is the coefficient. See on the equation 56, what is the coefficient of u? Is 1, right? And on the right hand side, the coefficients are 1 minus theta and theta. When I add it up, again it has to become 1. So I have no other choice. I cannot just simply take 1 minus theta and 2 theta. That will be inconsistent. Okay? So you understand that that's the consistency condition that you have invoked, that you have taken a part of theta. If it is overestimated, then the other part has to be underestimated, so that the two together would give you a quantum which is exactly what you want it to be. Of course, you can redefine a new variable. That's the easy part to do, right? So that's not difficult. So having obtained the equation that we have in the last part, so what I could do is I can multiply both sides by d plus theta L inverse, right? So that will give me the equation 58, right? So that's what we have done. We have just simply taken d L inverse. You can see the way we define the gain matrix is nothing but the coefficient of u of k minus 1. That's what we are doing. See, I have u of k minus 1. I am multiplying by g to get the new iterate, and that is precisely what we have here. So in 58, this whole thing minus k minus 1 constitutes your gain matrix. This we have done it. So now what happens? You can very clearly see how theta comes into play. because by a different value of theta, I could alter the eigenspectrum of the G matrix, right. So, for this Gauss-Seidel method, we can do that, and we can obtain the gain matrix as given by 59, and then we can fall back upon this theorem of Ostrowski and Varga, and this also requires something out of the A matrix that you have, the conditionality being that A has to be symmetric, okay. And alpha is positive. I just forgot to write that. And then what will happen, this gain matrix, which is now a function of the relaxation parameter theta. So, the gain matrix will have this eigenspectrum, the maximum of which, the spectral radius of that G of theta would be less than 1 if this A matrix is positive definite and theta is bracketed between 0 and 2. So, this is the driving observation that why capital theta has to be upper bounded up to 2. This comes from this theorem. Okay. Now, of course, once again you would find that many a times that this expectations from the property of A matrix are not obtained. So, we need to look for other iterative methods. If we do that, we try to calibrate the iterative methods by defining a quantifying parameter, which here we are calling it as the efficiency of the iterative method. So, the efficiency of the iterative method depends upon the following two sub clauses, that how much of work that I have to do in each iteration, that is what we are talking about, work required per iteration, that has to be compounded with how many such iterations I will have to do. That defines the total work, right, for overall convergence, and these two together should be minimum. That's precisely what we are aiming at. To understand how to calculate this will be a little beyond the scope of, but it is shown that if I keep on doing this iteration over many steps, then we can find out the error norm at k plus 1th stage when divided by the error at the kth stage almost becomes given by the spectral radius, right. This you have actually seen this equation in a somewhat different way when we did that. If you recall how the error at the kth stage was related to error at the initial condition, we found out that was related to lambda to the power m. So, that was there we had said that if it was a stationary linear iteration, we had the same set of lambda, and but what happens is if we adopt now the point of view that the G matrices are going to be different at different levels of iteration, like what you are going to go and give it to me even for the 3 by 3 system, then what you find that this spectrum of the G matrix will keep changing from iteration to iteration. But if you go over a large step, then you would find that it all balances out to the spectral radius of the equivalent linear stationary linear iteration, right. So, basically then you can see the importance of the spectral radius of this matrix plays a role in deciding how error you are reducing per time step, right. That is, if lambda of G is less than 1, then if I take a logarithm of that quantity, that will tell you how many decimal places that we have shifted the error to. Okay. So, that is why we define this rate of convergence as minus of log lambda to the base 10. So, minus is of course there to give it a positive flavor, because you know, I mean, if it is really convergent method, lambda will be less than 1 and log of that will be minus. So, that is what overall you get a positive quantity, right. Now, this was the kind of scenario that people were looking at for a long time. Then came this new method which is called the alternating direction implicit method, okay, ADI method. This was for some of you who are from chemical engineering would be happy to note that this was done by some people working in chemical engineering. It came out in mid 50s to late 50s. Eastman, Ratchford, Douglas, they are the major people developing this method. See what really happened. Now, if you look at it take a historic perspective, first we had this point methods, right? In the point method also we could take a Jacobi method or we could take a Gauss-Seidel method, right? We have seen that. Then we have seen that we could also solve it line by line, right? Then we had those line methods. Then we had this relaxation method. So the subject is progressing. So we have gone from point to line, and then from point to line to relaxation methods, and then this idea occurred to some people, like it's a boundary value problem. So all the boundary be incorporated as quickly as possible. See what is happening here. Here the boundary condition is slowly percolating as I am going up. Suppose I do it like this, that in one stroke I go from bottom to top, and in the next stroke I go from left to right. Then what happens? When I am going from this way to that way, I am bringing in this and at one go. This is being felt only when I almost come there, right? Now, if I take the sweep from left to right, this two boundary condition and this boundary condition would come to play right at the onset itself. So, in this alternative direction implicit method, ADI method, the name itself suggests that we will switch directions alternately. So, once I will go from, let us say, bottom to top, next I will go from left to right, and this is what is the basic idea. Now, let us try to explain it in terms of equation elliptic PD as given by this equation 60, and this is what is called as the elliptic PD in a self-adjoint form. So, basically self-adjoint form comes the way this A and C matrices, A and C appears in this equation, okay. So that you can discretize these terms in a manner so that the resultant matrix, you can invoke symmetry of that matrix. So the role of self-adjoint form in solving elliptic PD is quite central, and we will start from here in the next class.